Welcome to this explainer. Today, we're diving deep into the massive architectural complexity of high-stakes ticketing systems. You know, we've all been there, trying to snag a ticket to a hot show. But have you ever stopped to wonder what exactly is happening under the hood before you even enter your credit card? It's literally a delicate dance of data.
Think about it for a second. How in the world do thousands of people click buy on the exact same highly contested concert seat at the exact same millisecond without crashing the whole system, or even worse, without double charging someone? This is basically the ultimate concurrency nightmare of live events. And solving it? Well, that requires some seriously bulletproof system design.
So, let's jump right into the weeds here. The staggering complexity we're dealing with is wild. We're not just talking about firing up a simple web server in a database. No way. We're looking at a vast, interconnected web of microservices, intricate database schemas, and continuous event streams. All of this is required just to securely lock a single ticket without the whole thing falling apart. To get from a user clicking checkout to actually holding that seat, there are exactly 14 highly choreographed technical steps. 14 steps! It's an incredible engineering journey. And the kicker? If even one of these 14 steps fails or misfires, the entire transaction just completely falls apart. Now, these 14 steps don't just happen randomly. They build into a much larger overarching topology. The entire prepayment flow is actually divided into 4 distinct phases. And the single overriding goal across this entire progression is pretty straightforward. Safely transition a seat's status from available to locked, and simultaneously move a user's booking from none to payment pending.
Here's our roadmap for this explainer. We'll start with Phase 1, Event Discovery. Move right into Phase 2, Checkout Intent. Hit Phase 3, the Critical Lock, and wrap up the phases with Phase 4, Payment Orchestration. After that, we'll look at System Resilience, and finally, the final system snapshot. Let's get going.
All right, kicking things off with Phase 1, Event Discovery. This is all about browsing and checking the availability. Right out of the gate during event discovery, the system is getting absolutely hammered with high-throughput reads. I mean, millions of people just refreshing pages. To handle this without melting the servers, the Search API routes metadata requests over to OpenSearch, and availability checks go straight to Redis. The huge takeaway here? Absolutely no heavy inventory mutation happens during these simple searches. It's all lightweight, cache-driven, and lightning fast.
Moving right along to Phase 2, Checkout Intent. This is where we start handling those concurrent loads.
To process those checkout requests safely, we have to rely on a really fundamental engineering concept called idempotency. Basically, this is the property of an operation where applying it multiple times doesn't change the result beyond that very first attempt. This is absolutely crucial, guys. Think about network retries or those impatient users who just relentlessly hammer the buy button when their browser lags for even a second. We have to handle that gracefully.
So let's look at how this works in practice with an idempotency check. On one side, we have the happy path. That first request comes in, gets inserted into the idempotency table, and everything proceeds normally. But on the flip side, if a duplicate click comes in, the database immediately catches it via a hash conflict on that exact same key. It instantly rejects that duplicate with a 409 conflict error. Boom! This elegantly prevents double booking before we even touch the main inventory.
Now we're getting to the really good stuff. Phase 3, the critical lock, securing the seat.
This critical lock happens in 3 sequential make-or-break steps. First up, the booking service requests a hold from the inventory service. Second, the inventory updates using a super clever database mechanism called optimistic concurrency. And third, the system emits events to keep the rest of the architecture updated. Let's zoom in on that second step, because it's pretty fascinating.
To truly understand how we beat race conditions, check out this brilliant SQL update strategy used by the inventory service. There's a piece of logic there that essentially says, set the version to version +1. This is optimistic concurrency in action. It guarantees the seat wasn't silently sniped by someone else just milliseconds prior. If 2 requests hit this database at the exact same moment for the exact same seat, only one is going to successfully increment that version number. The other fails, 0 rows are affected, and the system knows instantly that the seat is gone. Right after that successful lock, we use something called the outbox pattern. Within a single atomic database transaction, the system decrements the available seat count, and at the exact same time, inserts an event record, a seat held event, into an outbox table.
That outbox is then reliably read by Kafka. Why go through all this trouble? Because it completely, 100% guarantees we never hold a seat without also notifying the rest of ecosystem.
And those notifications create these beautiful asynchronous ripples through the system. Kafka grabs that seat_held event and asynchronously updates our Redis cache. Yep, the exact same cache serving all those heavy search requests we talked about back in phase 1. The massive architectural takeaway here? This setup elegantly isolates the high-throughput search traffic completely away from our highly sensitive, highly transactional inventory database. It's a real game changer for scaling.
Okay, the seat is tentatively ours. Let's look at phase 4, payment orchestration. This is the handoff to the external gateway.
There's a crucial design note in the payments database schema that literally saves companies millions of dollars in refunds. It's a unique index applied directly to the booking ID column. By doing this, it guarantees at the foundational rock-solid database level that we will never ever create 2 payment orders for the exact same booking. It effectively stops double charging in its tracks, even if there are severe network hiccups or crazy retry loops. Let's step back for a second and look at the architectural synthesis of what we've covered so far. We really have to balance synchronous and asynchronous operations. For instance, the checkout API, that absolutely must be strictly synchronous. You simply cannot proceed to a payment page unless that seat is physically held in the database. But updating the Redis search projection, that can totally, safely be asynchronous. Eventual consistency is perfectly acceptable for discovery traffic, and it's what allows the whole system to scale so massively. Up next, system resilience. Because, let's face it, things fail, and we need graceful self-healing. Consider 2 common failure scenarios. On one hand, what if the external payment gateway completely fails right after we lock the seat? Well, the system triggers a compensating transaction. It immediately fires off a synchronous call to release the inventory, so the seat isn't artificially blocked from other eager buyers. On the other hand, we have the classic abandoned cart scenario. For this, a background worker constantly loops, checking for pending bookings where a 10-minute hold timer has expired. If a user just walks away from their screen, the scheduler automatically reclaims the seat and throws it right back into the available pool.
All right, let's bring it all together for the final system snapshot. This is our prepayment state.
This really is the climax of our explainer. Look at this synchronized, perfectly balanced state across all 4 independent databases. When a system is humming along like this, it is truly a thing of engineering beauty. So to summarize exactly what we're looking at right before payment, in the booking database, the status is set to payment pending. Over in the inventory database, that exact seat is marked as locked. Down in the payment database, the gateway order is officially created. And finally, over in Redis, the available seat count has been successfully decremented so nobody else thinks it's open. The seat is held, the booking is pending, and that 10-minute countdown clock has officially begun. But I want to leave you with this provocative thought. The seat is safely locked, right? The 10-minute clock is ticking down. But what happens to this incredibly precise architecture if that 10-minute timer runs out at the exact millisecond the user's credit card is actively processing with the bank? Does the seat release? Does the payment still go through? Think about the chaotic edge cases of a scenario like that. Until next time, keep exploring the fascinating world of system design.